Hello and welcome back. This is lecture 4 of the Thermodynamics course. Last time we looked at how a parcel of air changes temperature as it rises or sinks, and that parcel of air being unsaturated. And we looked at finding the potential temperature, and we looked at isentropic motions, which assume the parcel of air remains unsaturated. Today we're going to look at several different moisture variables and also look at how a parcel of air changes when it has moisture that evaporates into it or a saturated parcel of air rises. So we're going to be looking at the thermodynamics of water vapor and moist air. Starting off with different moisture sources, the moisture in the atmosphere, much of that moisture comes from evaporation from the oceans. There's also evaporation from lakes, rivers, and from the land. The moisture in the atmosphere is most concentrated in the lower troposphere, near the surface, since it is closer to the moisture evaporation region and temperatures are warmer. The warmer air has the capacity to have more moisture in it, so if the temperatures are warmer, more moisture can be evaporated into the air. As you go up higher in the atmosphere, it gets colder and colder, and there's not as much moisture in the air. Some unusual properties of water. One of those is that the solid floats in the liquid. As you can see, ice cubes float in the water when you have a glass of ice water. The maximum density of water is at 4 degrees Celsius. So as water cools down, the density gets greater and greater, but as it cools below 4 degrees Celsius, then the density begins to decrease. Water is also colorless, tasteless, and odorless if it's in its pure state. And almost anything can dissolve in water. Water can also absorb a large amount of heat, so it is slow in warming up and slow in cooling compared to other substances. It has a high surface tension, and the solid, liquid, and gas forms are all found naturally on the Earth. We're going to look at several different moisture parameters that are used in meteorology. Those are dew point, mixing ratio, vapor pressure, relative humidity, and the wet bulb temperature. And we'll start with the dew point. Dew point is defined as the temperature air must cool to at a constant pressure in order for the air to first become saturated. Dew point is a good comparative indicator for the amount of moisture in the air. So you can compare the dew point of two different locations, and you'll know which location has more moisture in the air. Here is a model image showing dew point on there. The contours of dew point are known as isodrosotherms, and I'm going to point those out on here. Where you have the most moisture is where you have this white line here and this orange line here. This is the 20 degree Celsius isodrosotherm, so the dew points are in the 60s and near 70 here in the southeastern United States. And as you go to the southwestern United States, the air is much drier. This red contour here is the 0 degree Celsius isodrosotherm. So in the southeastern United States, there's abundant moisture and a lack of moisture near the surface in the southwestern United States. So we can use dew point as a comparative measure for where in the United States there's more moisture and where there's less moisture. And up to the north, where you have colder air, you have some less moisture also, and the higher elevations tend to have less moisture. Look at the overhead camera, and I'll show you a simple experiment that you can perform that you can use to find what the dew point value is. The materials that you're going to need are, you're going to need a plastic cup, and you're going to need a thermometer. So we'll start off by diagramming our cup here, and you want to fill this plastic cup up. A metal cup will work good also, metal or plastic. Fill it up at about halfway with water, and then submerge that thermometer into that cup. And the water that's in here will be at room temperature. And it's best to perform this experiment on a day where the dew point is fairly high. If it's a cold winter day and the dew point is very, very low, if the dew point is below freezing, then this experiment is not going to work. And you may have seen this several times where you have a glass of ice water or a glass of cola with ice in it, and then you see the condensation that forms on the outside of the cup. That occurs because the temperature of the cup falls below the dew point. So what our object is that we want to find out how much cooling needs to occur to reach that dew point value. So we're going to have another cup out here that has ice water. You put ice H2O. And then see what the temperature is of the room temperature, H2O, and then gradually add ice water into this water here. And as you do that, the temperature is going to cool down. And keep looking at the thermometer and notice how much the temperature cools down. Once you start to see the condensation starting to form on the cup, then that is an indication that you have reached the dew point value. So this is a simple experiment that you can use to find what the dew point value is. Next, we'll go over the mixing ratio. Mixing ratio is the mass of water vapor divided by the mass of dry air. And it is plotted on the skew-T log P diagram. Dew point on the skew-T log P diagram is plotted using the isotherm. So you determine the temperature and the dew point by looking at the isotherm values on the skew-T. Just like with dew point, mixing ratio is a good comparative indicator for the amount of moisture that's in the air. Another moisture variable is vapor pressure. Vapor pressure is the air pressure produced from the water vapor alone, and it's going to have units of millibars. Vapor pressure is also a good comparative indicator for the amount of moisture that's in the air. Next, we'll look at saturation moisture variables. The saturation vapor pressure and saturation mixing ratio are found with respect to the temperature value. So that it's the maximum amount of moisture that can be in the air for that temperature. And for the vapor pressure, it's saturation vapor pressure. For the mixing ratio, it's the saturation mixing ratio. And these are used to determine the value of the relative humidity. The relative humidity is the percentage that the air is saturated. It can be found by the following formula. You take the mixing ratio divided by the saturation mixing ratio, multiplied by 100%, or you can take the vapor pressure divided by the saturation vapor pressure and multiply by 100%. So two ways there to find the relative humidity. However, relative humidity is not a good comparative indicator for the amount of moisture in the air unless the temperature information is also known. Because if you know the relative humidity and the temperature, then you can figure out what the dew point value is, and then you could compare the air samples that way. On the overhead, we'll look at how the relative humidity of the air changes as it rises or sinks, looking at an example of upslope flow and downslope flow. When you have upslope flow, where a parcel of air is forced to rise, the temperature of this parcel of air is going to decrease. Since the temperature decreases, then the dew point is going to be closer to the temperature and the relative humidity is going to increase. So our parcel of air here, for example, has a relative humidity here of 50%. And as it's lifted up further, it now has a relative humidity of 70%. It has the same amount of moisture in the air that it did here as it had here, but now the temperature and dew point are closer together since the temperature has cooled down. So rising air cools, and if it's unsaturated, it gets closer to saturation. And once it becomes saturated and it continues to lift, then precipitation will occur. The opposite occurs with downslope flow. Suppose we have a parcel of air 80% relative humidity. It sinks down. As it sinks down, it's going to warm up. Since the temperature warms up while the moisture in the air remains the same, the relative humidity value is going to decrease with the sinking of the air. So in summary, relative humidity increases as a parcel of unsaturated air rises and decreases as a parcel of air sinks. A rising parcel of air with a relative humidity of 100% will generate precipitation. Next, we'll look at wet bulb. Wet bulb temperature is produced by evaporating moisture into the air until it is saturated and then reading off what that new temperature is. Evaporation is a cooling process and adds moisture to the air. Thus, in unsaturated air, the wet bulb is less than the initial temperature and greater than the initial dew point. On the overhead, we'll take a look at an example of air that is initially unsaturated. It has a temperature of 50, dew point of 30. Rain falls into that air, and what happens is that the temperature starts to go down because you have evaporational cooling, but the dew point value goes up because you're adding moisture to the air. And generally the dew point will increase more than the temperature will drop. So once this air becomes saturated, then the temperature will even out, let's say for example, to about 44 degrees Fahrenheit. So the temperature has cooled down and the air is now saturated. And this is known as the wet bulb temperature, or TW. Next, we're going to look at a demonstration of temperature in the air and how evaporation can influence that temperature. I have several materials up here. I have a fan, and I have some water, and I have a thermometer, and I have several towels here that are going to be used. So our fan and our water, I'm going to first place some water inside of the bowl here. And then next I'm going to read what the temperature is in the room. The temperature in the room right now is about 65 degrees Fahrenheit. So 65 degrees Fahrenheit is the temperature. And when we turn the fan on and you put your hand out in front of the fan, you'll notice that it feels a lot cooler to your hand. It feels like the air has cooled down. But if we put this thermometer in front of the fan and see how the temperature changes, you'll notice that the actual temperature is not going to change that much. We started off at 65. We keep it in front of the fan, and however long you keep this thermometer in front of the fan, it is going to stay at that same temperature. Although, when I put my hand on one side of the fan, it feels warmer and it feels cooler on this side of the fan. So why does it feel a different temperature to the human skin? And there's two reasons why the temperature feels different to the skin. One reason is that the skin always has moisture on it. So when this air is hitting up against my hand, it's promoting evaporation. So the moisture that's on my hand is being evaporated at a greater rate as that air rushes by my hand. So I get some evaporational cooling from that. Also, we went over in the last lecture the transfer of heat. The temperature inside this room is 65 degrees Fahrenheit, but the temperature inside my body is much warmer than that, 98.6, much warmer. So there's a temperature gradient between my body and the surrounding air. And since the air is cooler, the heat wants to travel from my body towards the surrounding air. So when I put my hand in front of the fan, it promotes a quicker transfer of that heat, because it's taking the heat that builds up around my skin and removing it more quickly, so it makes it feel like it's cooler in front of this fan, although the temperature remains the same. The air temperature remains the same. We can promote a significant amount of cooling if we have much more evaporation taking place. Next, I have a towel here, and I'm going to soak that towel in some water. So I've now saturated the towel, and initially the towel had the same temperature as the room, 65. Now if we put this towel in front of the fan here, this towel is going to cool off, since there's a significant amount of evaporation that'll be occurring. So as I hold this towel and the moisture continues to evaporate, I'll put it on a higher speed to promote a faster evaporation process, and then all my stuff blows away. It starts to really cool off rapidly here. And how much cooling occurs, I can put that thermometer inside of the towel here and see how much cooling starts to take place. So I take the thermometer, put it within that towel, and then let that air blow into that towel. The towel cools down. So we have a latent heat process occurring here. We have evaporation, which is going to cool the surrounding environment. You're going from a liquid state to a vapor state, so the air molecules, the water vapor molecules, are gaining energy. And since they're gaining energy, that is going to take energy away from the surrounding environment. You're taking energy away from the surrounding environment in order to give those molecules, water molecules, more energy to evaporate. So if we keep our towel on here, the temperature is going to start to cool off over time. We'll keep that air cooling, keep the towel cooling. And this experiment will work best if the air is dry. If you have dry air, then you're going to promote much more evaporation, and so the temperature is going to cool off more. And the temperature is starting to cool off. It's cooled off a couple of degrees, and if you keep it there for an extended period of time, it'll continue to cool more and more, and then it'll come to a point where it'll no longer cool down anymore. And it'll no longer cool down once you're getting close to the wet bulb value. And also, when you're doing this experiment, make sure your fingers don't get too close to the thermometer, since they're going to add a little bit of heat to that, because my hands are warmer than this towel is. And so the temperature now has cooled down to 60 degrees. It started off at 65, and now it's 60. Let's see if we can zoom in to that thermometer and see if we can detect what the temperature is on there. Where you see the green, the bottom of the green was 70, and the bottom of that yellow is 60, so it's right at 60. And the temperature continues to fall even further. But once we take this towel away from it, then there's no longer evaporation, and the temperature will start to warm back up again. So we'll keep that there and see if the temperature will start warming back up. And I can turn, although it doesn't matter whether I have the fan on or not, the temperature of the room is going to stay about the same. As I said, it was about 65 initially, so eventually the temperature is going to warm back up to 65 degrees. And in a minute here, when it's warmed back up to 65, I'll show that to you. We'll look at some other moisture variables in meteorology, the absolute humidity and the specific humidity. The absolute humidity is the mass of water vapor divided by the volume. So it is the density of the water vapor. And the specific humidity is the mass of water vapor divided by the mass of moist air. The wet adiabatic lapse rate abbreviated WALR. The wet adiabatic lapse rate is the rate of cooling of a rising saturated parcel of air. So in the last lecture we looked at the dry adiabatic lapse rate. In this lecture we're going to look at the wet adiabatic lapse rate. The dry adiabatic lapse rate was a constant, but the wet adiabatic lapse rate is not. The value of the wet adiabatic lapse rate is not a constant, but will range from about 4 degrees C per kilometer to near the dry adiabatic lapse rate if the air does not have a lot of moisture in it. And it averages about 5 degrees Celsius per kilometer. Some other information about the wet adiabatic lapse rate. Warm rising saturated air will condense out more precipitation than cold rising saturated air. And this is because the latent heat release is greater in the warm saturated air. The warm saturated air has more moisture. Thus, when the moisture condenses out, more precipitation will be condensed out. So this is why warm season convective type precipitation will have much more moisture that falls out of the clouds than when the clouds are cold, such as a wintertime rain event. The wet adiabatic lapse rate is about 4 to 5 degrees Celsius per kilometer in rising warm saturated air and greater than 6 degrees Celsius per kilometer in rising cold saturated air. Next, we'll go over the concept of latent heat. Latent heat is the addition or subtraction of heat from a substance without it undergoing a temperature change. It is also a substance changing molecular configuration without it undergoing a temperature change. The surrounding environment changes temperature, but the moisture in water does not change in temperature unless it's acted on by conduction. Examples: ice stays at 0 degrees Celsius as it is melting or freezing. Water at sea level remains at 100 degrees Celsius while it's boiling. And if you spilt some water on the ground, that water over time will eventually evaporate away. But that water will stay at about the same temperature as the environment that it's on. The evaporation process, if it's slow enough, it won't produce much cooling. In the example that I showed with the fan, the evaporation is occurring so rapidly that you can detect a significant temperature change. The temperature will decrease with the evaporation. And we can go back to the thermometer now, and we'll see what temperature that it is up to now. Remember, the bottom of the green was 70. There we go. We can see now it's about in the middle of that yellow range there, so it's getting closer to 65 degrees, which was the initial temperature of the room. So we've demonstrated there that evaporation will cool off the temperature. A good example of that is if it's a warm day outside and you go swimming and you get out of the swimming pool, it can feel significantly cooler, especially if there's dry air outside. You may get goosebumps. It feels very cold. That's because of that rapid evaporation. The same thing when you get out of the shower in the morning. That rapid evaporation makes it feel a lot colder. So in summary of latent heat, when the temperature of a substance remains constant during a latent heat process, but the environment is going to change in temperature. And on the overhead camera, look at latent heat absorption. Again, an example of that is rain falling into dry air. And this is a critical concept in operational meteorology in a winter weather situation because it can change rain over to winter precipitation. Suppose the air near the surface, we have a temperature of 35 degrees Fahrenheit with a dew point of 10 degrees Fahrenheit, and then rain falls from aloft. Let's say we have an upper level disturbance and rain falls from aloft. and then it falls down to the surface. As this rain enters this dry air, it's going to begin to evaporate, and it's going to cool off to the wet bulb temperature. If the precipitation is heavy enough and lasts long enough, the temperature will cool all the way to the dew point. Will cool all the way to the wet bulb temperature. So, and remember, the wet bulb temperature is between the initial temperature and dew point. So if the air temperature is 35 with a dew point of 10, then, for example, let's say that the air cools off after complete evaporational cooling to 28 degrees Fahrenheit. And so we determine that to be our wet bulb temperature in this situation. Also is important what the temperature of the soil is too. That can have a little bit of influence on what the temperature changes to. So now, we initially had a temperature of 35, which would just be a cold rain, but after evaporational cooling, it's now 28 degrees. So we'll at least now have a freezing rain, and it could change over to sleet and snow also, depending on the depth of the cold and warm layers in the troposphere. If it all goes completely below freezing, then it's likely to turn over to snow. If there's a warm layer aloft, it could be sleet, but we'll at least have freezing rain, be a winter weather event. So during a latent heat absorption process, the surrounding air cools or does not warm as much as it otherwise would. Processes include evaporation, melting, and sublimation. And we just saw in our example of a latent heat absorption process where the air cools. Latent heat release. During a latent heat release process, the surrounding air warms or does not cool as much as it otherwise would. And I'll go over what I mean by does not cool as much as it otherwise would. Processes for latent heat release include condensation, freezing, and deposition. We'll go to the overhead camera and look at a latent heat release process. We have two parcels of air here. One is at 10 degrees Celsius, so this is the temperature in Celsius, and at the bottom is the dew point. So we got a 0 degree Celsius dew point, 10 degree temperature. This parcel of air initially starts off as being saturated at 10 degrees Celsius and 10 degrees Celsius. Temperature and dew point. We're going to lift this parcel, both these parcels of air up 1 kilometer. This parcel of air that's unsaturated will continue to be unsaturated after it's lifted 1 kilometer. It'll have a new temperature of 0 since it's going to cool at the dry adiabatic lapse rate, which is about 10 degrees Celsius per kilometer. So we raised 1 kilometer, so we cooled it off by 10 degrees. The dew point, even when the air is unsaturated, is going to decrease at 2 degrees Celsius per kilometer. So the air is still unsaturated here, and it's cooled off to 0. Look at this parcel of air here that started off where it was saturated. It did not cool off as much. It's been lifted the same amount of distance, and it started off with the same temperature, but this parcel of air is warmer. It cooled by 5 degrees Celsius as it decreased from 10 to 5. And when air is saturated, the dew point decreases with the temperature. So both the temperature and dew point both decrease by 5. But what's another important information about this parcel is that it's warmer than this parcel, so there is not as much cooling. So that's what I meant by a latent heat release process. It does not cool as much as it otherwise would. It did not cool all the way to 0 like this parcel did. It only cooled down to 5 because you had latent heat of condensation release in this parcel. So if you start off the more moist and closer to saturation this parcel is near the surface, then the warmer it's going to remain as it rises up due to that latent heat release. So in a thunderstorm type environment where you have instability and unstable atmosphere, it helps to have moist saturated air near the surface. The amount of energy in a latent heat process is different depending on what the process is. Vaporization and condensation have 2.5 times 10 to the 6 joules per kilogram. Melting and freezing release and absorb a less amount of energy, just 3.34 times 10 to the 5th. So there's a big difference here. If I can point this out, that the power of each one of these is different. This was to the 6th power, and this one was to the 5th power. So this one is much more energy. So in evaporation, vaporization, condensation influence the temperature in a parcel of air more than when melting or freezing occur within the parcel of air. So if it's snowing and it starts to melt, the evaporation of that snow is going to cool the air more than the melting will, although both of these together will help produce a cooling. The sublimation and deposition release and absorb the amount of energy that's equal to the addition of these first two. So we have 2.83 times 10 to the 6 joules per kilogram. We just added these two together since we're skipping that intermediate process, going straight from a vapor to a solid or from a solid to a vapor. And on the overhead, we'll look at the difference in the latent heat release between a cold, moist parcel of air and a warm, moist parcel of air. We'll first look at a cold, moist parcel of air. So we have a sounding where at the surface the temperature and dew point are both near freezing and the air is saturated. And the parcel of air is written on the sounding, and I'm going to darken that in. So the parcel that's drawn on the SQT log P sounding, that's the temperature trajectory a parcel of air will take if lifted from the surface to high and to the troposphere. These dashed lines on here are the moist adiabats. And notice that they have different slopes. In the warm air that we have here, this is 20, 30 degrees Celsius, the slope is much more upright. So you do not have as much cooling that takes place. But here, where you have colder temperatures, the slope is greater. The slope is closer to that of the dry adiabats. So you're not releasing as much latent heat when the parcel of air starts off colder. So this parcel of air doesn't have too much of up and down slope like it would if it started over here. And we'll look at that next. We have a warm, moist parcel. And I'll draw this parcel in from this sounding. Notice how much more straight up and down it is. So it does not cool off as much. So if the parcel is warmer than the surrounding environment, it's going to continue to rise. And in this case, it does. A significant distance here, after this parcel is lifted up far enough, it'll be warmer than the surrounding environment and it'll rise on its own. So if the parcel starts off warm and moist, it has a greater chance of rising on its own due to positive buoyancy. But in this situation, this is more of a snow type situation where you're going to have, to generate precipitation, you're going to need force lifting take place. And there's not as much latent heat being released, so you're not going to generate as much precipitation as you are in this situation. It'll generate much more precipitation here. Next, we'll look at the vapor pressure equation. This is known as the Clausius-Clapeyron equation. This is one of my most favorite equations in meteorology. When the temperature is known, the Clausius-Clapeyron equation, or we can abbreviate it CC equation, can be used to find the saturation vapor pressure. If the dew point is used, then we can find what the actual vapor pressure is. And on the overhead, we'll take a look at the Clausius-Clapeyron equation. It's the natural log of the vapor pressure divided by 6.11 is equal to L, latent heat constant, which is 2.453 times 10 to the 6 joules per kilogram. You'll remember that value that we just saw earlier for vaporization, divided by gas constant for moist air. Since we're looking at just the water vapor, we using the gas constant for just the water vapor, the RV, which it has a constant value of 461 joules per kilogram. So those two constants can be divided by each other to produce a new constant. Then these two constants are multiplied by 1 over 273 subtracted by 1 over T. The temperature that's plugged in the Clausius-Clapeyron equation has to be in units of Kelvin. And again, what's being found is the vapor pressure in millibars. So you plug in the temperature into this equation and solve to find the saturation vapor pressure. If you put the dew point in for the temperature here, then you find the actual vapor pressure. So if you know the temperature and the dew point, you can find the vapor pressure and the saturation vapor pressure. And this is the equation that is used to find the relative humidity. So the relative humidity is not simply the temperature value divided by the dew point divided by the temperature value. You have to first plug the temperature and dew point both in this equation, find what the vapor pressure is, and find what the saturation vapor pressure is, and then divide them by each other and multiply by 100%. An important point, the saturation vapor pressure increases at an increasing rate as the temperature increases. That's saying the same thing as warm air can have more moisture within it. And that relationship that we're going to look at here, I have different temperatures and then solving the Clausius-Clapeyron equation to determine what the saturation vapor pressure is. So if we point this out, starting from the top, we have a temperature of freezing is 6.1 millibars. We go up to 5 degrees Celsius is 8.7. But as the temperature continues to increase, this value of saturation vapor pressure begins to go up very rapidly. By the time we get to 30 degrees Celsius, we're up to 42.1 millibars. So that's showing that relationship of that exponential type relationship. The more the temperature increases, the more moisture that can be in the air. And we'll look at another display of this on the overhead, where on this one I've started with a temperature of minus 10 degrees Celsius and then gone up to 40. At minus 10 degrees Celsius, the capacity for moisture in the air is only 2.9 millibars, very low, but up at 40, it's 73.8. If we convert that to a Fahrenheit temperature, 14 is 2.9 millibars, and typically the air is not going to be saturated when it's this warm, up at 104. But if you were finding the relative humidity, you'd need to know what that saturation vapor pressure is. If it's a very hot temperature, 104 Fahrenheit, that would be 73.8 millibars. Next, look at the mixing ratio and vapor pressure equations. You'll need these equations when solving many of the problems in the exercises for the course. And I'll point this out. The mixing ratio equation, W, is 0.622 times the vapor pressure divided by the pressure minus the vapor pressure once again. So you need to know what the vapor pressure is and the pressure, and those two bits of information can be used to find what the mixing ratio is. We can rearrange this equation to solve for E, where E, the vapor pressure, would be the mixing ratio times pressure divided by 0.622 plus the mixing ratio. Supercooled water. Supercooled water is liquid water that has a temperature below freezing. Supercooled water in the atmosphere is very common. The vapor pressure over supercooled water is greater than that over ice at the same temperature, and this has very important implications in meteorology. And the implication we'll go over with the Bergeron process. So if you have a mixture of supercooled water and ice at the same temperature, the ice grows at the expense of the supercooled water. This is an important precipitation growth mechanism. We'll look at the overhead camera and go and look at the Bergeron process. We have several diagrams that we're going to go over this process because it can be difficult to understand, so I'll go over several different ways of trying to help you understand this process. So over here we have ice crystals, and suppose that the relative humidity is 100% with respect to the ice crystals. So in this case, the temperature is equal to the frost point. TF is the frost point. Or here with the water drops, the relative humidity is 100% with respect to a liquid. So in this case, the temperature is equal to the dew point. And on the skew-T log P, it only has the temperature and dew point value on the sounding. It does not have the frost point. What's very important to understand here is that the frost point is not equal to the dew point. So in our Bergeron process here, the frost point is actually going to be greater than the dew point. Since E, the vapor pressure, is higher over a liquid surface as compared to an ice surface at the same temperature. That's right, why the frost point is greater. You don't have to cool it off as much to reach saturation with the frost point as compared to the dew point. So suppose that we have air here, and it's a mixture of water droplets and ice crystals, and the temperature is -5 with a dew point of -5. So the relative humidity is 100% with respect to the liquid, but with respect to the ice, the relative humidity is greater than 100%. Since the temperature is below the frost point. So you actually have a supersaturation condition with respect to the ice. But as I mentioned on the sounding, it's only going to have it with respect to the liquid. So this is going to produce a vapor pressure gradient between the water and the ice. Just like with atmospheric pressure, the air tends to flow from high pressure towards low pressure. Well, it's the same concept with water vapor. The vapor is going to want to move from higher vapor pressure toward lower vapor pressure. So surrounding the water, we have more water molecules. This is liquid water. It's surrounded by more water molecules. Since the liquid water can support a higher vapor pressure, and suppose that this water and ice are at the same temperature. So this water here is supercooled, and we have ice here at the same temperature. Even though they're at the same temperature, you're going to have more water molecules that are able to evaporate away from this water surface. It's more difficult for the vapor to discharge from the ice surface. It's more difficult to go from a solid to a gas than it is to go from a liquid to a gas. So the vapor pressure around the ice is less than that over water. So you have a vapor pressure gradient where these vapor molecules want to move towards where the ice is. Once these molecules move towards the ice, then supersaturation occurs with respect to the ice. So if we take one of these molecules here and move it to where the ice is, it suddenly becomes supersaturated, and thus the molecules start condensing onto the ice, and the ice builds up in mass while more water molecules are evaporated, leave the water surface, and move toward the ice. So the ice grows at the expense of the water. And now we're going to examine the Clausius-Clapeyron equation to investigate this concept further. This is the same equation that we looked at earlier, the Clausius-Clapeyron equation. One is going to be for liquid water, and the other one is going to be for ice. For liquid water, we use LV, that latent heat of vaporization that we looked at earlier, 2.45 times 10 to the 6th. But when you're looking at ice, the saturation vapor pressure, you do not look at the vaporization, you're looking at a sublimation type process. So it has a different constant for L, and this is L sub S, which is 2.83 times 10 to the 6 joules per kilogram. So since these constants are different here, that's going to have implications on what the saturation vapor pressure is even when the temperatures are the same. So the saturation vapor pressure over ice at minus 10 degrees Celsius is 2.6 millibars. But over the liquid, it's 2.9 millibars. And so we can determine what the relative humidity of each one of these is with respect to ice and with respect to the liquid. First, with respect to the liquid, the relative humidity is 100%. The vapor pressure and saturation vapor pressure are both 2.9 millibars. But with the ice, we have a difference in the saturation vapor pressure. We end up with a different saturation vapor pressure because we use that different constant for L in the equation. So we ended up with only 2.6 millibars for the saturation vapor pressure. So when we find the relative humidity with respect to ice, it's 2.9 divided by 2.6 times 100, which gives a relative humidity of 112%. So with respect to ice, it's supersaturated, so the ice grows at the expense of the liquid. Next, we'll look at the frost point. The frost point is the temperature air becomes saturated with respect to an ice surface. Frost point is higher than the dew point since air will be supersaturated with respect to an ice surface before the temperature cools all the way down to the dew point. And we'll look at the overhead at a skew-T sounding, and you'll notice this many times on the skew-T when the air is saturated. It's a rain event or a loft. It may be snowing, it's cold enough, and then turns into rain as it approaches the surface. So no matter what kind of precipitation is occurring, you'll often notice if the clouds extend through a deep layer of the troposphere that closer to the surface, the temperature and dew point of the air will be about the same. And then you'll notice that the temperature and dew point lines spread apart as you go up higher into the troposphere. Remember that the temperature and dew point here is calculated with respect to a supercooled water surface, but the temperatures up here are well below freezing. In fact, at this point here, the temperature was at freezing. It was 0. So above this, all this cloud up here is below freezing. And definitely when you get below minus 10, minus 20, this is all ice crystals up here. And although it does not appear that this air is saturated because the temperature is not exactly equal to the dew point, it actually is, because the frost point is greater than the dew point. So if you moved all this dew point line over to the right at a warmer temperature, then it would represent saturation with respect to an ice surface. So this air is saturated even though there's a little bit of a dew point depression there. So on upper level observations, which is 700, 500, 300, they'll blacken in the station plot if the dew point depression is 5 or less. One reason they do that is because even though it may be 3 or 4, where the dew point is not equal to the temperature, with respect to an ice surface, it actually is saturated. The skew-T log P only uses saturation with respect to water or supercooled water, thus dew point is plotted and not the frost point. Implications: frost can develop on the ground before the dew point is reached. An air that is sub-freezing with a small dew point depression, as we looked at on the skew-T log P, is likely saturated with respect to ice. Next, we'll look at the virtual temperature. The virtual temperature is the temperature dry air would need to have the same pressure to have the same density as air with moisture. Virtual temperature is greater than the actual temperature because air with moisture is less dense than dry air at the same temperature and pressure. We'll go to the overhead camera, and I have a diagram that will help solidify what this concept is here. So we have the virtual temperature. Suppose we got two parcels of air here. One is moist and one is dry. So this one has more moisture in it, but it has the same temperature. The densities are going to be different because the moisture in the air is going to influence what the density of the air is. The moist air is less dense. So the density of number one, we have the dry air here, and we have density 2 of the moist air here. So the moist air is less dense. So the density of 1 here, the dry air, is more dense, higher density. So we want to add enough heat to this parcel so that the densities become equal, so that density 1 is equal to density 2. The temperature at which that happens is the virtual temperature. So the new temperature of the dry air is the virtual temperature. So again, the densities are different here. The moist air is less dense, but we want to warm this air up so that it has the same density. And once we do that, then we have the virtual temperature. The use of the virtual temperature simplifies thermodynamic equations, since the virtual temperature can be used in dry air equations and the moisture is still represented in the air. And there's equations for the virtual temperature. We'll look at the one on the bottom. We have the virtual temperature is equal to the temperature times 1 plus 0.61 times the mixing ratio. So if you know the mixing ratio, which is an indication of the moisture in the air, multiply that by 0.61, and that mixing ratio will be in kilograms per kilogram, so it'll be a small number. So you'll add 1 to a small number, so the number will be a little bit greater than 1, and multiply that by the temperature. It needs to be in kelvins also to determine the virtual temperature. Next, the equivalent